Statistics is concerned with making inferences about a population. We do that by conducting statistical experiments. The statistical experiment is any process that we go through that generates a set of chance outcomes. Now, before, when we were talking about sample spaces, we were talking about making a list of all of the possible outcomes when we conducted a statistical experiment. Now, sometimes it's really helpful to us to take a look at our sample space and to assign numbers to the elements in our sample space. When we do that, we're using a thing called a random variable. A random variable is a function that assigns a value, a real number value, to every element in our sample space. Now, take for example, I'm tossing a coin 3 times. And when I toss that coin, I really am only concerned with how many times does heads appear. So heads could appear 0 times, 1 time, 2 times, or 3 times. And how many times it appears, that's the value that I'm going to assign by use of a random variable to each of my elements in my sample space. Sometimes when we're assigning values to the elements in our sample space, we're concerned with more or less the answer to a yes or no question. An example of this is the product defective or not? So I take a shipment and I'm going to take a sample of 8 products from my shipment, and I'm just checking, is it defective or not? I'm going to give it a value of 1 if it is defective and 0 if it's not. Now, when we do that, when we assign a value of just 0 or 1 to an element in a sample space, and we do that for every element in the sample space, then what we've done is we've assigned a Bernoulli random variable. Now, random variables can either be continuous or discrete, and we can tell which one it's going to be based on looking at the sample space. If a sample space has a finite number of elements in it, or it has a countably infinite, so think about being able to sit and count the elements in the sample space, and you could actually count them all if you had enough time in some kind of linear fashion, then it's called a discrete sample space. And the random variable that we use to assign values to that sample space is called a discrete random variable. Now, on the other hand, sometimes random variables are continuous, and we also tell that by looking at the sample space. So, if the sample space has so many elements in it that you couldn't possibly count them all in some kind of linear fashion, you think about trying to count how many points there are on a line segment, and like there's always a point between 2 other points, and then you count that one, and then there's a point between that one and another one, and you just can't count them all because it just spirals out of control. It's uncountably infinite. Then you have a continuous sample space, and the random variable that assigns values to the elements in that sample space is called a continuous random variable. We're going to talk about discrete random variables first. Now, discrete random variables assume that there's some probability assigned to each of the values that the variable may take. A simple example of this is a random variable that can take the value of 1, 2, 3, 4, 5, or 6, simulated by rolling a die. And the probability that's assigned to each of the outcomes is 1/6. Venturing into probability with our discrete random variable, we can make probability distributions, cumulative probability distributions, and probability histograms. Probability distributions are also known as probability mass functions and probability functions. All of these represent the same thing. For each of them, they're a set of ordered pairs, x, f of x, where f of x is going to be greater than or equal to 0 for all of the x values. The sum over all of the x values of f of x is going to equal 1, and the probability that our random variable has the value of lowercase x is f of x. So what these really are is ordered pairs of the value of the discrete random variable as the first part of our ordered pair, and the probability of that value as the second element in our ordered pair. So whenever we're asked to check if something is a probability function, probability mass function, probability distribution, what we really need to check are these three things: that the ordered pairs are the value of the discrete random variable and the probability of that value, that the sum of all of the probabilities equals 1, and that each probability is greater than or equal to 0. Now, when we talk about the cumulative distribution function of a discrete random variable, what we're doing is we're taking and we're adding together all of the probabilities that the random variable takes on a value less than some value x. And that's the value that we assign to our function f of x. Let's consider a simple example of rolling a die. So when we roll the die, it can have outcomes of 1, 2, 3, 4, 5, or 6. Those are all possible x values for my random variable. Now, if I consider f of x in my probability distribution, what this is the probability of each of those numbers occurring. So the probability that I roll a 1 is 1/6. The probability I roll a 2 is 1/6. A 3 is 1/6. A 4 is 1/6. A 5 is 1/6. And a 6 is 1/6. So this right here is my probability distribution. And I could write it out as the ordered pairs 1 1/6, 2 1/6, 3 1/6, 4 1/6, 5 1/6, and 6 1/6. And that would be another way of representing my probability function. Now, if I want my cumulative distribution function, now when I'm looking at the cumulative distribution function for discrete random variables, I end up with a piecewise function that's actually going to have one more piece than I have possible values for my random variable. The first piece is always going to be for the value of my random variable being less than the smallest value that it takes on. Then I'll take values of my random variable that are greater than or equal to the smallest value and strictly less than the second smallest value. And I'll progress this way until I've reached the top value. So I have 3 less than or equal to x less than 4. 4 less than or equal to x less than 5. 5 less than or equal to x less than 6. Then I have my final entry where x is greater than or equal to the largest value it takes on. For the first entry, since my random variable can't take on a value less than the smallest value it takes on, then the probability is 0 that that happens. Then moving along, the probability that my random variable takes on a value between 1 and 2, with 1 included, well, my random variable can have a value of 1, and that has a probability of 1/6. That's the only way that it's between the two. So I have a value of 1/6 there. Now, the same thing happens between 2 and 3 with 2 included but 3 not. The probability that my random variable is in that window is 1/6. But we're dealing with a cumulative distribution function, so what it's going to do is it's going to add together the probability that I'm in this window plus the probability that I'm in the last window. So I'd have a value of 1/6 for this window plus my 1/6 from above. So I would have a total of 1/3. And now I move on to the next window, and again, the probability that I'm in the window of 3 to 4 with 3 included and 4 not is 1/6. But since I'm dealing in a cumulative probability function, I'm going to add the value above. So I'll add the 1/3, and I'll have a total cumulative probability of 1/2 when my random variable is between 3 and 4. And then moving on to the next step, again, that I'm between 4 and 5 with 4 included, 5 not included is 1/6 plus the 1/2 that I had above. So I have a total probability, cumulative probability of 2/3 in the 4 to 5 window. And then between 5 and 6, 5 included, 6 not, I have 1/6 plus 2/3 from above. So I have 5/6 as my cumulative probability in my 5 to 6 window. And finally, x greater than 6, including 6, is 1/6 as well. And I'll be adding to that the 5/6, which gives me a total cumulative probability of 1. So one of the things that we like to do with these is plot them so that we can see on a graph what's happening. So on my first, I have a value of 1, 2, 3, 4, 5, and 6. And the probability is somewhere between 0 and 1. And we're specifically going to care about 1/6 because that's where everything falls for my probability distribution. So here's my probability distribution as a graph. So I have 1/6 as the probability of getting 1, 1/6 as the probability of getting 2, 1/6 as the probability of getting 3, 1/6 as the probability of getting 4, 1/6 as the probability of getting 5, and 1/6 as the probability of getting 6. Other times, what we actually want is the histogram. So to turn a probability mass function plot into the histogram option, all we do is we make bars that have the max height of the probability where they're centered at the value that the random variable takes on. So this one's very easy to make because it's the same value straight across. But that is our probability histogram. Now it's also sometimes helpful to graph the cumulative distribution function. So with this one again, my horizontal axis will be labeled with the possible values for my random variable. So I have 1, 2, 3, 4, 5, and 6. And then I'll have my y values. I know that my probability has to be between 0 and 1. And I know that I'm going to end up with cumulative probabilities between 0 and 1 in increments of 1/6. So when I plot my cumulative distribution function, I know that if x is less than 1, so everything right up to 1 but not including 1, so I use an open circle at 1, then my value is 0. And now I know between 1 and 2, my cumulative distribution, 1 is included, so I put a closed circle there and an open circle at 2 because it's not. But any x value, any value for my random variable between 1 and 2 is going to have a cumulative probability of 1/6. And then I do the same thing between 2 and 3, bumping up to 1/3 as my y value. The same thing between 3 and 4, bumping up to 1/2 as my y value. Bumping up to 2/3, same thing between 4 and 5. And bumping up to 5/6, same thing between 5 and 6. And then finally I get to, at 6, a value of 1, and that continues on forever. So whenever I plot a discrete cumulative distribution function, it's going to look like a step function. Whenever a random variable is continuous, we need to deal with continuous probability distributions. Now, conceptually, perhaps the most challenging thing with the continuous probability distribution is the idea that the probability of the variable taking on a single value is 0. So what I mean by that is the probability that x equals a number, say 5, so the probability that x equals 5 is going to equal 0. Now, your gut instinct to that is probably, no way, that can't be. It makes no sense. So let's think about what a continuous random variable really means. So continuous random variables allow the value of the random variable to take on any value on a spectrum, any real number. So when I think about something as having the value of 5, I'm saying that it has the value of exactly 5, not any one of the infinite number of points between, say, 4.9 and 5.01, other than 5. Or not any of the infinite number of points between 4.99999 and 5.00001, other than that 1 out of an infinite number of points, that is 5. So if I start thinking about this idea of the random variable can take on this infinite number of values so close to 5 that we can't perceive it as being anything different than 5, but it really, in fact, is different than 5, then the likelihood that we actually choose exactly 5 from that infinite number of other possibilities, that probability being 0, it starts making a little more sense. Now, we're going to take a look at some of the math that's going on when we calculate these probabilities using our continuous probability distributions, and it's hopefully going to make even more sense why that value is 0 at that point. The math involved here is integral calculus. If you're feeling a little bit rusty with integral calculus, you might want to brush up on that before you get into too many of the examples with this. So please, by all means, take the opportunity to brush up on that if it's making you feel uneasy at all, the idea of integral calculus coming back right now. Let's first take a look at the definition of a probability density function. The function f of x is a probability density function, or a PDF for short, for the continuous random variable capital X defined over the set of real numbers if we have the value of our function is greater than or equal to 0 for all x in the real numbers. The integral from negative infinity to infinity of our function f of x is equal to 1. And the probability that our random variable takes on a value between a and b is equal to the integral from a to b of f of x dx. Let's take a look at the example where we have a function f of x equals x squared over 3 whenever x is between negative 1 and 2, and it's 0 everywhere else. Now we're asked to verify that this function is a probability density function, and we're asked to find one of the probabilities from it. So let's first look at verifying that it's a probability density function. So to do so, we're going to use the definition, and we're going to show that these 3 attributes are true of this function. So the first attribute, we need f of x to be greater than or equal to 0 for all x in the real numbers. So whenever x is outside of the negative 1 to 2 range, the function is 0, so it's definitely true there. So then we just need to consider, is x squared over 3 positive, or 0, for everything between negative 1 and 2? So you can do this multiple ways. You could graph it. You can just plug in some values. We can notice that x squared is in our numerator, and our denominator is positive. Whenever we square a number, it is positive, and a positive number divided by a positive number will be a positive number. So there's no way that negatives will enter this equation. So our function satisfies this. All right, so the second thing that we need is we need the integral from negative infinity to infinity of f of x dx to equal 1. So we need to know if this is true. So to figure out if it's true, we should take this integral. So if I take the integral from negative infinity to infinity of f of x dx, now this function has two different values depending on where we are on our real numbers. So this is going to equal the integral from negative 1 to 2 on this window of values. We have our function taking on the value x squared over 3 dx. And then everywhere else, our function is 0. So from negative infinity to negative 1, I'd be taking the integral of 0. And from 2 to infinity, I'd be taking the integral of 0. Now remember, when we take integrals over different intervals and they don't overlap, we can add them together to get the integral of the whole space. So the integral over all of the real numbers is going to be the sum of these three integrals. So the integral from negative 1 to 2 is one that we're going to have to do a little bit of work on, so let's just leave it the way it is right now. The integral from negative infinity to negative 1 of 0, well, the integral of 0 is 0, so that's really just 0. And again, the integral of 0 is 0. So really what this all comes down to is the integral from negative 1 to 2 of x squared over 3 dx. So when we take this integral, remember we're going to add 1 to our exponent. So I have x cubed, and then I'm going to divide by my new exponent. So I'm dividing by 3, and that's what's in my numerator. And I still have an over 3 in my denominator. And I'm going to be taking this from negative 1 to 2. So I can simplify this to be x cubed divided by 9 from negative 1 to 2. Now remember, when we're taking definite integrals like this, we take the maximum value and we plug it in. So I have 2 cubed over 9. And we subtract from that the min value plugged in, so negative 1 cubed over 9. So when I do this arithmetic, 2 cubed is 8. So I have 8/9. Negative 1 cubed is negative 1, and minus a negative is plus. So I have plus 1/9. And 8/9 plus 1/9 is 1. So I get to check this off. My integral from negative infinity to infinity is in fact 1. Now finally, the last part of this that I have to verify is that the probability that my random variable is between a and b is the definite integral from a to b, f of x dx. Now, this is often given somehow in the context of the wording of the problem. And so we didn't look at the wording behind this problem, but the wording in this problem tells us that this is what gives us the probability. And so we can check this off. Often that's what we'll be able to do with that third option. So the big things to check when we're checking to see if something is a density function are 1 and 2. And if we want to know if it actually represents probability, then we need 3, and 3 will often be given in the context of a problem. Well, the next thing that we were asked to find is the probability that a random variable takes on a value between 0 and 1. So we actually can use this third part of our definition right here to do that. So we're going to take a definite integral from 0 to 1. Remember, in a definite integral, whether it's less than or equal to or simply less than, the max value stays the same, so it doesn't matter that this is less than or equal to and this is less than. So we'll be taking our definite integral from 0 to 1 of our function here. Let's take our definite integral from 0 to 1 f of x dx. And now let's look at what part of our function are we looking at. So we're looking for x values between 0 and 1. And all of 0 and 1 fall in between -1 and 2, so we'll be using this first piece of our piecewise function. So we're taking the integral from 0 to 1 of x squared over 3 dx. Now again, we take our integral and we add 1 to our exponent and divide by it. And I'm taking that over the interval 0 to 1. And now I do some arithmetic, simplify it a little bit. I've got x cubed over 9 over the interval 0 to 1. I'll plug in my max value and have 1 cubed over 9 minus my min value, 0 cubed over 9. So I'll end up with 1/9 minus 0, or just 1/9. So my probability that the value falls between 0 and 1 is going to be 1/9. So the math behind the probability taking on a value of 0 for exactly 1 point, we have this idea that with a continuous probability distribution, that the probability that, say, a is less than x is less than a, right? And we can throw an equals to or not, it's fine. It's going to equal the integral from a to a, f of x dx. If we take a look at the function that we had before, we would have taken the integral and we would have gotten x cubed over 9 evaluated from a to a. And if we plug a in, we get a cubed over 9 minus a cubed over 9 is going to equal 0. So the fact that a definite integral, when evaluated from one value to that same value, is 0, that's the math behind the probability of a random variable taking on a single value being 0. Now we also have the concept of a cumulative distribution function, f of x, for a continuous random variable x with density function f of x. All right, so we're using capital letters for our cumulative distribution function, and our density function has a lowercase f there. That's our notation idea. What this is going to tell us is the probability that our random variable takes on a value up to x, that it's less than or equal to some value x. And to find this, we take the integral from -∞ to our value x of our density function, f of t dt. And we can do this for any real number x. Let's consider our density function that we had in our previous example, and let's work with it to find our cumulative distribution function that relates to this density function. So to do that, we're going to follow our definition of our cumulative distribution function. So capital F of x is going to equal the probability that our random variable is less than or equal to x. It's going to equal the integral from -∞ to x for our f of t dt. All right, we need to take an integral from -∞ to x. This is going to be the integral, since we have different pieces, everything from -∞ to -1, our function's value is 0. So we'll take an integral of 0 dt. Then we'll add to that an integral from -1 to x of t squared over 3 dt. Now, if we work this out, again, the integral of 0, regardless of the bounds, is going to be 0. So we have 0 plus the integral from -1 to x of t squared over 3 dt. So working out that integral, I have, just like I had before, I'll end up with t cubed over 9 evaluated over the interval -1 to x. So when I evaluate this, I get x cubed over 9 minus -1 cubed over 9. Now, I can't simplify anything about x cubed over 9, so I'll leave it the same. And I have -1 cubed is -1, so minus -1 is going to be plus 1 over 9. And now I have like denominators, so I can put my numerators together and have x cubed plus 1 all over 9. So what I have is my cumulative distribution function, capital F of x, is going to equal x cubed plus 1 over 9. Except this is only true when x is between -1 and 2. If it's less than -1, then I'm only going to be dealing with this part of my integral, where I have the integral of 0. So it'll be 0. So I actually have it 0 if x is less than -1. And now if it is -1, I can put the equal to either place. I do need to account for the -1, so I need an equal to one place or the other, but either way, I'm going to end up with 0. So put an equals to wherever you'd like. And now I also need to deal with x values greater than 2. Let's take a look and see what happens if I plug in 2. Well, my density function takes on a value of 0 if it's greater than 2. So that means it's no longer contributing anything to this cumulative distribution function. Remember, the cumulative distribution function is the total probability. So if the density function is no longer contributing anything after x equals 2, then I need to have the probability all the way up to 1 by the time I get to 2. And I can double check and make sure that I actually have by plugging 2 in for x. And if I do that, I get 2 cubed, which is 8, plus 1 is 9. I get 9 over 9, which equals 1. So I have a probability of 1 at that point. And again, I have to account for when x equals 2, and I can put it either place I want because plugging 2 into my function in the middle gets me the same value 1 here. So now let's revisit this idea that I want to know the probability that my random variable falls between 0 and 1. So with a cumulative distribution function, if I take f of 1, this is going to tell me the probability that my random variable takes on any value up to 1. But I don't care about the values that are less than 0. So what I can do is I can subtract out my cumulative distribution up to 0. So what I've done here is I've taken the probability that the random variable is any value up to 1 minus the probability that the random variable is up to 0, leaving me only the probability that the random variable falls between 1 and 0. When I plug in my values, I can use my piecewise function here, and both 1 and 0 fall into this middle piece. So I'll plug in, I'll have 1 cubed plus 1 over 9 minus 0 cubed plus 1 over 9. And I'll do this arithmetic, simplify it out. I'll get 1 cubed plus 1 is 2 over 9 minus 0 cubed plus 1 is 1 over 9. And 2/9 minus 1/9 is 1/9, which agrees with our answer that we got when we used our probability density function. So we can actually use the cumulative distribution function or the probability density function to find the probability that a continuous random variable falls in some interval of possible values.